Bismillah ar-Rahman ar-Rahim. I am Ahmed from Ashour, Arab Academy for Science, Technology and Maritime Transport. I will present my paper under the name of Efficiency Improvement using Adaptive Hybrid Modulation with Coding and Frequency Selection Scheme for Future 5G Wireless Network, which has the following outline. The outlines are problem statement, objective, literature review, hybrid MQM LFSK or HQFM system, simulation and results, conclusion, future work, and references. Problem statement. According to channel conditions, bad, clear, or noisy, the non-conventional adaptive modulation systems switch between BBSK, QBSK, 16 QM, 64 QM, or more, with different spectral efficiencies to overcome these conditions. By increasing the distance between the mobile equipment and the base station, the signal-to-noise ratio is decreased, resulting in a selection of less bandwidth-efficient modulation scheme, thus leading to fewer bit rates. The objective is keeping higher spectral efficiency for more regions inside different mobile cells in adaptive modulation schemes, when increasing the distance between the mobile equipment and the base station. Literature review. For hybrid modulation schemes, most of previous literature considered the hybridization of multiple modulation schemes, but neither of these schemes considered the combination of orthogonal FSK and MQM, except paper number 2, 3, and 5. For adaptive modulation systems, most of previous literature considered the using of PSK and QM schemes, and neither of them used the adaptive hybrid modulation schemes. Hybrid MQM LFSK or HQFM system. Traditional bandpass modulation techniques include amplitude shift keying, phase shift keying, and frequency shift keying. The hybrid of both ASK and PSK is called QAM, quadrature amplitude modulation. The hybrid of both FSK and QAM is called hybrid QAM LFSK modulation or hybrid quadrature frequency modulation. If the modulation frequency changes according to some of the transmitted bits, a third dimension will appear in the signal space diagram as shown in figure 4. In this manner, higher dimensions of QAM signals can be divided into lower dimensions of QAM signals with separate orthogonal frequencies. Therefore, the symbols lying in each plane don't interfere with other planes as shown in figure 5. HQFM transceiver. The HQFM transmitter is shown in figure 6. A part of the transmitted bits N-K bits are used for generating the carrier frequency using the non-coherent LFSK modulator, and the remaining K bits are used for mapping the I and Q symbols using the conventional MQM modulator. The output of the two multipliers are summed to generate the hybrid signal as shown in figure and shown in equation 1. The HQFM receiver consists of two stages. In the first stage, a non-coherent detection of FSK frequencies can be done by using a bank of bandpass filters, followed by envelope detectors. And after detecting the correct carrier frequency, which represent the N-K bits, the remaining K bits can be detected coherently in the second stage by using an ordinary MQM demodulator. Simulation and results. The hybrid LFSK and MQM system described earlier has been implemented using the Simulink environment for real-time simulation as shown in figure 8. The design can be extended to any FSK and any QAM size. Figure 9 shows the transmitted data, the transmitted 4 and 16 hybrid signal, and the received data. It's shown that the hybrid signal includes 4 frequencies due to 4 FSK modulation and 3 amplitudes due to 16 QAM constellation, and there is a delay time of 42 bits between the transmitted and the received data to compensate the processing delay time caused by this. Performance analysis of the hybrid signal. Power spectral density. The spectrum of the hybrid signal can be approximated as shown in equation 2. It depends on the number of FSK frequencies L and the size of QAM M. The theoretical spectrum of the 4 and 16 hybrid signal, 4 FSK and 16 QAM are shown in figure 10, which show that the main loop of the hybrid signal occurs at normalized frequency 0.41. which is greater than 16 QAM and less than 4 FSK. Thus, it's a bandwidth efficient modulation. The simulated spectrum of the same schemes are also shown in figure 11. Since the first null of the 4 and 16 HQFM spectrum occurs at 0.41, then the normalized null-to-null bandwidth is 0.83, and by setting the parameters of the hybrid system to be as shown for the bit time and frequency separation, then it will meet the orthogonality condition in equation 3. The theoretical null-to-null bandwidth of the hybrid system is 10.04 kHz. The simulated null-to-null bandwidth is 10.2 kHz, thus verifying the same theoretical results in figure 10. The bandwidth efficiency of LMHQFM is given in equation 4. It lies between the bandwidth efficiency of LFSK and MQM, where it's directionally proportional to M and inversely proportional to L. At negative 20 decibel, the simulated 4 and 16 HQFM bandwidth is 8.5 kHz, and therefore the simulated bandwidth efficiency will be 1.4, which is close to the theoretical value, which is 1.5. Error rate performance in additive wide Gaussian noise channel. The bit error rate probability of hybrid quadrature frequency modulation is approximated as shown in equation 5. Theoretical and simulated bit error rate results of the 4 and 16 HQFM compared with other conventional 4 FSK, 16 QAM and 64 QAM schemes are also shown in figure 15. The figure shows that the simulated bit error rate of the proposed system is almost like the theoretical bit error rate results obtained from equation 5. Also, the 4 and 16 HQFM system's performance is better than 16 QAM and 64 QAM, but degraded when compared to the non-coherent orthogonal 4 FSK. So, the performance of LMHQFM is better than LQAM and LMQAM. Thus, it's a power efficient modulation scheme. Channel coding in HQFM system. The bit error rate performance of different block codes such as Hamming, Reed-Solomon, and extended Goulet codes and hard decision convolutional codes with different rates have been applied to the hybrid system and shown in next. Figure 15 shows that the bit error rate performance of Reed-Solomon code is better than Hamming and extended Goulet code and outperforms the hard decision convolutional code with a rate of half for EB by N node less than or equal 9 decibel only. Adaptive hybrid L by M HQFM system. The proposed adaptive LFSK and MQAM system can switch between different hybrid modulation schemes according to the estimated signal-to-noise ratio values as shown in figure 16. The theoretical and simulated bit error rate performance of the proposed adaptive system is shown in figure 17, which is compared with conventional adaptive MQAM. It shows that the efficiency of the adaptive hybrid scheme overcome the adaptive MQAM scheme in most EB by N node values. The switching thresholds are also shown in table 1. Adaptive hybrid MCFS scheme. It's known that the value of the signal-to-noise ratio in the link budget equation depends on fixed and variable parameters as shown in equation 6. By replacing S by EBRB and N by N node B, then equation 6 can be rewritten as shown in equation 7. It's seen that in equation 7 that EB by N node depends on variable parameters such as path loss and bitrate. The idea of the proposed scheme is fixing the value of EB by N node in the adaptive hybrid system in different regions of mobile cells. This is achieved by fixing the value of path loss in the link budget equation and keeping the rest of parameters constant. Firstly, we calculated the value of the path loss in the mid-range of each cell type at 3.5 GHz using the recommended ITUR propagation models for indoor and urban outdoor environments. In the next step, we plotted the effect of changing the carrier frequency in the band of 2.8 up to 5.8 gigahertz versus the distance with respect to the calculated path loss as shown in figures 18. The recommended values of signal to noise ratio versus distance from different cells are used to plot EB by N node versus distance at constant frequency FC equal 3.5 gigahertz. Then we used the data from previous figures to plot figure 20, which show the effect of constant path loss on different cell types in the adaptive L by M HQFM system. Assume that the mobile equipment exists in an femtocell and moving away from the base station. According to the distance between the mobile equipment and the base station, the adaptive system selects the appropriate modulation scheme as shown in figure until it reaches the area where path loss is constant, thus keeping the spectrum efficiency constant to be 1.5 for more distance 4 meters, which is 10% of the femtocell area, thus improving the average spectrum efficiency of the femtocell. So if the mobile equipment keeps moving away from the base station until it reaches the picocell, microcell, then the macrocell, the proposed adaptive system select the appropriate modulation scheme and apply the same procedures, thus improving the overall spectrum efficiency of the system. This scheme affects on all scenarios except line of sight microcell and line of sight macrocell. Differential coding scenarios can be applied to the adaptive hybrid system to form a new adaptive hybrid modulation with coding and frequency selection scheme, which can increase the coding gain of the overall adaptive system. Figure 21 shows that BCH with N equal to 15 and K equal to 7 can increase the performance of the adaptive hybrid system than the uncoded one by increasing the spectral efficiency of the femtocell, picocell, and non-line of sight macrocell only. Conclusion: the proposed MATLAB simulating for the 4 and 16 HQFM system verify the theoretical equations of power spectral density, bandwidth efficiency, and bit error rate. Different block and convolutional coding schemes have been applied to the proposed system to increase its efficiency. An adaptive hybrid L by M HQFM scheme was proposed to increase the system's throughput than the conventional adaptive schemes. The proposed adaptive hybrid MCFS scheme can increase the average spectrum efficiency of the overall system. The adaptive hybrid MCFS can also be easily implemented by using the software-defined radio systems due to their flexibility and ability to be used for highly adaptive communication systems by simply downloading a program file which can switch between many adaptive hybrid MCFS scenarios for more enhancement. Therefore, the adaptive hybrid MCFS is expected to be a promising adaptive technique for the 5G cellular network. Future work: MATLAB simulating based L by M HQFM system can be applied for other fading channels like Gaussian and the Nakagami channels. Research can be directed to the use of non-coherent, non-orthogonal, coherent orthogonal, coherent non-orthogonal FSK. Possibility of using Gaussian shaped FSK can also be explored in this context. Non-coherent hybrid star QAM FSK modulation can be employed to draw results. Turbo coding schemes with different rates and constraint lengths can also be applied in the HQFM system to maintain higher coding gain. Other coding schemes can also be applied to the proposed adaptive hybrid MCFS system to enhance the spectral efficiency of the proposed scheme. References: Thanks for your attention. Any questions?